if the CMRR is large, what it is saying is that this amplifier has a very good is very good at amplifying signals that are different and reduce or not amplify signals that are the same. So ideally, the common mode gain is usually less than 1. Anywhere between 0 to 1. That's a common mode gain. While your differential gain is in the hundreds of thousands. So what you find is that if you find that the common mode gain and the differential mode gain are closer for one transistor, are small as compared to another transistor, where that the CMR is big. Then it means that the second transistor with a big CMRR is performing better than the one with the smaller CMRR, because it is now rejecting signals that are common and amplifying signals that are different at the input than the first transistor. And therefore CMRR is a measure of how well the transistor is rejecting signals that are common and amplifying signals that are different. Any question? And if you do, you can see that on the page on the next slide. That's exactly what I'm saying. That the ability of an amplifier to reject a common mode signal, that is unwanted signal, while amplifying the different signal is what the CMRR is. So the CMRR is not just a formula, but it's actually a measurement parameter to see how well a transistor is rejecting noise or rejecting common signal and amplifying differential signal. And you see the bullet point second to last, it said the higher the CMRR, the better in which the ohm loop gain is high and the common mode gain is low. And the last bullet point says that the CMRR is expressed usually in decibels, in dB. The aspect of decreasing with frequency, we shall see that when we start to look at frequency response of an amplifier. Are there any questions?
Everything good, sir.
All right, everybody seems so quiet tonight. Am I confusing you guys so much that you don't understand what's happening, or you're so into it? That's why I'm happy that I sent this stuff before. You guys are all into. Ladies, how are you so quiet today?
Sir, them belly full, sir.
Also, I'm probably asleep. Seeing that then call niggeritis. That full. I mean, What's going on with you ladies tonight.
It's
Yes,
the other way around. No correct, the other way around.
The other way around, you're too hungry to talk. All right. So far, so good. All right, let's jump into the other part of this. Happy that people are understanding so far. So we'll talk about the offset voltage. Unless you want me to refresh, but it's right here. Offset voltage. Remember, I'll talk about offset voltage. Normally, the output of a transistor for operation amplifier is 0 if the input is 0, right? But realistically, a small DC voltage will appear and the output when there is no input or there is no input that is applied. Remember? I said that? And this is,
Yes, sir.
and thus differential DC voltage is required between the inputs to force the output voltage to be 0. So one way of making the output voltage to be 0 is to force the input voltage to actually be 0. Because remember, you don't have any input voltage initially, right? So we're saying that we're offsetting. That is the offset input offset voltage. So we're putting a voltage at the input of the transistor to make sure that when we look at the output, or when we measure the output of the transistor, that output voltage is really 0. Do you understand?
Yes,
Sir,
sir.
go again, sir. Sir, go again.
Okay. So we established already that if we have no voltage at the input, ideally we should have no voltage at the output. But that is not what is happening in the reality or in reality. In reality, what's going to happen is, even if we don't have an input voltage in a transistor, we're going to have an output voltage because of the internal movements of the electrons. Remember?
Yes, sir. Yes, sir.
Okay. Now that is the case, we know we're going to get an output voltage even if we had no input voltage. But we don't really want the output voltage because that's gonna throw us off when we're measuring, not true?
Yeah.
Okay. So to be sure that our output voltage is really 0, yeah, we have to correct that process from the inside. And we can not have to, but we can correct that process from the input side. Meaning, put a meter on the output. With no input voltage, we see what the output voltage is going to be when we look at a meter, right? Keep the meter on the output, and then we tweak the input until we tweak the input voltage across the 2 input terminals until we see the output voltage becoming 0 on our meter. And when we do that, that voltage at the input that we use to tweak the voltage at the output to become 0 is what we call our input offset voltage, because it is that input voltage that we're placing there now that is going to cause our output to now become 0. So that's what we're using to offset the output, or to make the output become 0 as it should be when we do not have an input voltage. So that's what is called an input offset voltage.
So, sir, in a scenario like that, no, right, sir? If you know the input voltage you will want to apply, sir, you will take that offset and subtract it or take the difference between it and then apply it for the input.
That's right.
Okay.
So that way, you will know what exactly your voltage, your amplification factor is going to be. Because you are now taking, okay. So it's like saying, all right, I'm going to fill this cup of water. But I already know that to fill this cup of water, the cup full is going to go up to 8 centimeter high. Or if you want to use liquid measurement, 8 grams, right? But you already know that you are putting in 1 gram of water on in the cup, and then you start to full from that 1 until it reach 8. So the reality is that it's really 7 that you're actually putting in, not true? And then so that 7 gram of water that you add is what's going to make the cup full. When you already have an offset, or when you have an offset of 1 gram of water already. You follow what I'm saying?
Oh, sir, just to clarify, this is like an overall term, or you use it in terms of each terminal, each input terminal?
I'm sorry, I didn't get the question fully.
Like for op amp, does it have one offset voltage, or you have one for each of the different inputs?
No, no. Remember that you're tweaking both inputs. In that case, you got to tweak the inputs. Or you can put one on ground and then you tweak the other one to know what the voltage is going to be that will offset or make the output voltage be 0. So each operational amplifier will have its unique offset. What manufacturers already have done is they know what this is already. So they'll tell you again in their specification sheet that for this operational amplifier, the offset input voltage is going to be, or is X amount of volt, 0.1 milliamp or a millivolt or something like that. So they will tell you. Follow me? So it simply means that you have to put that voltage into the transistor, or on the input of the transistor, for the output to really be 0. And then anything from there, because you know the reference point, or you know the reference already. So anything from there, you will also know. You just take away the reference from whatever your input, and you know what is the real input that is going in. And therefore, when you get an output, you know that the output voltage is really the offset, that voltage minus the offset voltage. And therefore, you'll know what the gain is.
Or based on that too?
Yeah.
All right, sir. Thanks, sir.
All right. So again, for everybody, so that we don't get confused so early, the input offset voltage is a voltage that you're going to be putting at the input side of the amplifier to ensure that the output voltage is going to measure 0. Because we already know that it will not measure 0 under normal circumstances because of what is happening inside of the transistor. And if you know what your input offset voltage is, it helps you, because you already know. It's like saying, okay, I'm traveling from Montego Bay to Kingston. But I'm already in Ocho Rios. currently I'm in Ocherius. So therefore, to know how much miles I'm going to travel to Kingston from Ocherius. Sorry, to know how much miles I'm going to travel from Montego Bay to Kingston. I'll have to take out the journey that I've traveled already from Ocherius to Montego Bay. Or Montego Bay to Ocherius. I'll have to take that out. That's my reference. That's my offset. You understand me?
Yes, sir.
Good. All right. Now the amplifier, operation amplifier, we have two voltages that we're applying to the input. We can apply the voltages to the to the inverting input or to the non-inverting input. If we apply a voltage there and we have resistance, you know current is going to flow. Okay? So we're going to have two input currents. But there's some things you're going to be learning about operator amplifier, which sometimes it's going to be a little bit confusing. But it's just how the operator amplifier is in terms of understanding. All right. So notice here we're talking about the input bias current of the operation amplifier. The input bias current is going to be the current on the two inputs divided by 2. In other words, it's the average current at the input. And the reason we need to know the input bias current is because we can actually apply an input offset current. Similar to what we did for the input offset voltage, we can apply input offset current to reduce the output voltage to 0 when you did not apply input voltage. We're going to look at that again in details because there's some other things we're going to be looking at where that is concerned.
Hold on, sir.
Yes.
What if one of those inputs was grounded, right? So you only had one input current. Would the input bias be just the 1 divided by the 2?
No, because there'll be down 2.
So it just
It
be
will
that.
only be it will only be the, you have to focus on the current that's going in.
All right, sir.
As I said before, it's a lot more than that. But we're going to go into that in detail because we have a whole half a chapter on that by itself. Okay? This really is a part of what helped to confuse the process of operation amplifier, because the truth be told is that, remember what I think we say? The operation amplifier input resistant is going to be what?
Ideally, it would be in infinity, but you say what, 20?
Very high.
Yeah.
Would be
It's going to be very, very high. You don't have to put a figure to it because every manufacturer has a different value. So if you apply a voltage to the input, causing current to start to head towards the input. If the input impedance is very high, then current is going to go into the amplifier, not true? Because current are like high impedance, eh?
Yes, sir.
Okay. And therefore, the truth be told is that there's no current that goes into the amplifier. So then how does it provide amplification? We're going to look at that again. All right? In details. Just remember some of the things. The input impedance, output impedance, what happens with them. All right, I want to skip the offset, input offset current, because as I said before, we're going to go into that in detail. We're going to prove these. So we're not just going to tell you that these are so, we're going to prove them. All right, these values is highlighted in blue. We're going to prove them from first principles. But that's after we understand a bit more about the transistor, about the operation amplifier. One thing we need to understand is that the operation amplifier, remember we said that it is a very, very high gain amplifier, yes? Yes. Very, very high gain amplifier, right? So if you apply a small signal input, it has a very high gain. What do you think is going to happen to the output?
You have a high output, sir.
Very high output, right?
Yeah,
Okay.
because the output is equal to the gain times the input.
Absolutely. But the problem is, there's not much, if any, meter that you're going to be able to measure such a high voltage on. In other words, the output voltage is going to be so high that it's going to be, it's not even going to be able to measure it. It drives the output is driven into what is called saturation. So remember, when something cannot hold, it basically overflow, right? With saturation, right? Think about a cup when it's or a sponge when it's saturated. What happens? They add more.
Sir.
You just run out so you can suit it anyway.
It is decode, sir.
So if you're if a sponge is the measuring, is what you use as your measuring device, then it simply means that if you're trying to measure the water in the sponge, when it becomes saturated, really and truly you're not going to be able to measure it because it's actually more water than what you're measuring because the sponge is saturated and overflowing, eh? So you're not going to be able to catch some of the water that is going into that sponge, eh? So in other words, you're not getting quite the value as what you're supposed to get because of the fact that it is not, when it's saturation, you're not capturing it. You only can go up to a certain level, capture a certain amount of water content, and that's what is in the sponge at the time. But anything beyond that, you're not really capturing it. So you don't really know how much more water was the sponge was exposed to, agree? No comment?
Yeah, man, sir. Yeah, man.
Okay. All right. So what we're saying is that when you operated the operation amplifier in such a way that you're applying input signal, doesn't matter which one of the input you want to use, the amplifier is amplify the signal and the signal is outputted. The output signal is going to be extremely large. And an extremely large output voltage, you might not be able to measure it on your normal multimeter. That's what I'm talking about. So the multimeter is what you're trying to use to do the measurement, but you can't really measure all of it because the output voltage is so high, eh? So really, truly, what is happening is that you're just seeing the signal going up to a certain level, and that's it. You're not seeing anymore. Or if it fluctuates and goes down, it goes down to a certain level and you're not seeing anymore. But you know, because of the sharp cutoff, you know it's not complete. It's not a true reading. So you can't say, boy, the water in the sponge is only the sponge when it's saturated is only the water that was captured, eh? So it's the same thing. You can't say the meter reading is on at this voltage, it's maximum. The maximum reading on the meter. It's you now are seeing that meter reading is exceeded by the output voltage. So you say that it's been driven to saturation. Well, what we're saying here is that a transistor, in this case, operational amplifier, is operating in what is called an open loop configuration. And in the open loop configuration, because the gain of the amplifier is so high, the output voltage is driven to saturation. And we're talking about open loop. We're looking at open loop right now on screen. There's nothing that puts a part of the output voltage back to the input. So it's called open loop. So the gain is very high because it's an open loop gain. And the only time we operate operational amplifier like that is when we are operating it as what is in the configuration known as comparator. Operated as a comparator. Okay? Again, we're going to look at that in detail. The information is actually in the group on the group page already, classroom, but we're going to look at that in detail. So, otherwise, the operational amplifier has a feedback. It's operated with a feedback. That is, a portion of the output is sent back to the input through a feedback mechanism. Okay? And that's what is happening right here. That's what I was trying to describe before. So don't look at the so you see when it starts operating with the feedback, with a loop, so notice the feedback, a portion of the output signal is fed back to the input signal. So you put in the input here, goes into the amplifier, amplified, outputted, and then they feedback a portion back to the input. In this case in particular, as I said before, because of such a high gain of the amplifier, look at what's happening on the output. The output is this graph, B. The signal actually will go up to a maximum output voltage and down to up to a maximum and down to a maximum, right? This is the input and this is the output. And what's happening is that there is a measurement at the output as to the amount of time or the time it takes to go from the minimum to the maximum value. And that's delta T. And what's the voltage change? The voltage change will be from here to here, which will be delta V. From here, from the bottom here, from here to here, will be the change in voltage. While the time it takes to go from minimum voltage to maximum voltage is what's called delta T. So the slew rate means the rate of change of the voltage to go from minimum to maximum over the time it takes for that to happen. as it's called the slew rate of our operation amplifier. Again, we're going to use that a little later, but we just need to make you understand what that means. Now, let's jump to some things, other things quickly.
Sir.
Yes?
So I'm trying to follow what you're saying. You said that.
With the slew rate?
Yes, sir. So basically, the amplification isn't linear. It's like there's some proportionality. There's not an instant transmission. I mean, it's like it doesn't just. It takes a amount of time to move from one state to the other, I guess, but in a very short amount of time.
Yeah. In other words, the time it takes for the voltage to change from minimum to maximum or the input, yeah, is not instantaneously. It has to go through the transistor for processing, eh? So it will take that time. Some people call it delay time. Some people call it propagation delay. They have different time. But the slew rate is, okay, and I want it to be very, very clear. The slew rate is measuring, is the measurement at the output, because you're doing the same thing on the input, you know. If a signal is a square wave, it's gonna go from minimum to maximum, right? But the slew rate is the same thing. The time it takes to go from minimum to maximum at the output voltage, over the rate of change of the voltage. So the voltage is going to go from whatever minimum value this is to the maximum value. So that's why if you notice the formula here, slew rate is delta VO, and delta VO is what? V plus minus V, right? So this minus this, that's what delta V is. This one, maximum plus minus the maximum, the minimum minus, right? So that's what delta VO is. And delta T is the time it takes to make that transition. So that's what is called slew rate.
All right, sir.
Okay. All right. So here's an example. If you want to know the slew rate, we want to do a calculation of the slew rate of, let's say this was the amplifier's output. You notice that from the minimum value to the maximum value, the changes, the linear aspect of the change. See, you realize the linear part of the change. In this case, it moved from -9 to +9. How long did it take to, and this is V out, of course. How long did it take? It take 1 microsecond. Therefore, the slew rate is the difference between -9 to 9. Yeah? So that will be 9 plus 9, which is 18 over 1 millisecond. And therefore, the slew rate is 18 volts per microsecond. All right, we covered these already. Operation of the transistor, type of operation, single-ended, double-ended, common mode. But this is what happens inside of the transistor. And I'm gonna leave it with you guys right here. It is very simple. Here it is, the two transistors. This is the basic of basics of the operation amplifier. You notice connectivity? You have one transistor which is connected to V1, one input, the other transistor V2, the other input, and the output. Remember how many outputs the operation amplifier has?
Is it one, sir?
One. We realize what
One.
happened? There are two outputs. There are two outputs from two transistors. So what happened is that the two outputs are superimposed, and that superimposed output goes to one output. That's why I have one output, right? So in other words, you realize you're getting a gain from one transistor plus a gain from another transistor that are superimposed, and therefore, if this is giving you a high gain and this is giving you another high gain, then it means that the gains plus the gains is supposed to give you a higher gain. If the signals are different at the inputs, all right? So this is what the basic circuit looks like. This is what this is the same circuit. Here it's not showing you the outputs being tied, it's showing the outputs being separated. But for this circuit, based on what we know already, if we had values for them, we could actually look at the DC biasing of the basic operational amplifier circuit. See, the DC analysis. So the DC analysis, this is how we do it. Remember we talk about taking the loop. Remember in devices 1, we got transistor, we took the loop.
Kirchhoff, sir, using.
We take the loop, we take the input loop and then we take the output loop. So if you're looking at it, DC analysis, this is how we get. So this VCE, all right, so where's the input loop for argument's sake? The input loop for this, sorry, I don't have a marker right now. What it
Should
do,
be the basis, sir.
it starts from here, go through here, incorporate here, and come back around here. So that's the input loop. Okay? The output loop, of course, would be
VCE. So
this come through here, back through here, and that's for one. We're looking at one transistor individually, right? So what we find is that from the input loop, we find that VCC, so if you're taking it this way, because VCC is minus, so if you're going this way, so VCC plus IERE, so IERE plus a minus V. So we have nothing connected to the base right now. So it will be VBE. Remember we're talking about input loop, right? Remember that we have a voltage across here. VBE plus IERE minus VEE equal to 0. Because that's Kirchhoff. Kirchhoff said the sum of the voltage in a loop equals 0, right? Or the supply voltage equals to the drop of the voltage around the loop. So that's how we get this equation. And from this equation, we can find what IE is. From this equation, we found IE. And because of the fact that we know IE is approximately equals to IC, but we have two ICs. We have IC up here and we have IC here. So therefore, IE over 2 is what will give us IE, right? Since BE is 0. So there's no voltage here. So again, going back to the law, this from here, we can actually write the output loop again. This is the output loop equation, right? Remember, I just showed the output. So for example, for this, the output is this is 0. So it's this, cross here, and come back here. Okay? So it's VCC minus ICRC minus VCE minus IERE. Okay? But IE is the same as IC. But we're using two transistors, that's why it's IE over 2. That's why I have this is IE over 2 and it's IE over 2. Now, there's something I need to tell you about this circuit. One last thing before we go. Very, very critical. Ladies and gentlemen, you see with this network? If you apply voltage here, at the VCC, the voltage this is a emitter bias configuration. And not emitter bias. That is emitter common emitter configuration. So the emitter is common to both the collector and the base, right? If you apply a voltage here, that voltage is amplified and inverted here. But if you apply a voltage here, that at the emitter, the voltage is amplified but not inverted. Because remember, IC and IE is approximately equal, right? But they're opposite in terms of phase. Now, because of this connection, what will happen is that this current, the current will be split. Some current will go here and some current will go here. And the current that will be going here is enough to flow right through this transistor, especially if this one is 0, and go, and there's an output voltage, amplified and outputted right here. So even though you don't have any voltage here, if you apply a voltage here, you still get a voltage at V2, VC2. And likewise, if you apply a voltage here, this is grounded, you're gonna have a voltage here because of the voltage applied at VB2, and you're gonna have a voltage here also because of what you apply. And that's because the two emitters are tied together. Okay? And that's why we have IE over 2, because actually it's 2 emitter current. It's IE divided by 2 because the two transistors two transistors are utilizing the same common emitter. They're tied to one emitter, so that current is going to be divided by 2. That's how we get this value, IE over 2. All right? Spend the time, look at the equation, and look at how they actually work this out. Just explain to you, look at how they work this out and how they got the values for this circuit. Okay? These are DC values right now, ladies and gentlemen. This is where we talk about biasing the transistor before we start to apply the AC signal, as you see here. Okay? And then we look at the AC analysis, which we're going to look at as of next week. We're going to look at the AC analysis.
Sir, last question, sir. So it's not a network, because I want to see 2 transistors in this up. So I'm wondering if you can make an op-amp with those 2 transistors, or
yeah, but the gain is not going to be great. So if you notice in right, you notice in this network, see the amount of transistors you have? 1, 2, 3, 4, 5, 6, 7. You notice the amount of transistors?
yes, sir.
That is why the gain is going to be that great. But if you only have 2, then you're going to have an increase as compared to what you'd have gotten normally. But it's not as great as if you have the more transistors, the greater the gain is going to be. What is important is to look at how it is configured. It's not just one transistor output being the input to our next transistor, which we call cascaded. But actually, what it is done is that it utilizes the common emitter by tying two transistors emitted together, so that when you have a signal here, that signal is not only giving you output voltage here, but it's actually giving you output voltage over here as well. And likewise, for this transistor, it's the same thing. And when you have them both superimposed to come out on one output, then you find that the output voltage is going to be much greater than if you had one transistor that was acting by itself. All right. Next time we meet, ladies and gentlemen, we're going to start to look at some of the circuits. So what I want you to do for me is to look at how these questions were. So this is the given circuit. This is the answer. I show you how you get to the equations and what you need to use to work it out. So next time we meet, we're going to look at the AC analysis. And AC analysis, we're going to look at that one, see what is done for it, and see how we actually work a problem with the AC analysis. Okay? And then we're going to move on to looking at some of the circuits, the basic circuits that the operational amplifier is used to create. So we're going to look at inverting amplifier, non-inverting amplifier, integrator, differentiator, summing amplifiers, etc. Okay? That you have already in the classroom. So what I'm going to ask you to do for me is to go, read ahead, watch ahead, integrate in. So we're going to look at, again, inverted amplifier, non-inverted amplifier, integrated amplifier, differentiator, summing amplifier, and that is as a starter. There are several other types of amplifiers applications that we're going to be looking at. Operational amplifier applications.
Sir,
Yes, sir.
you mentioned Mr. Wright would be coming in one of the sessions to
Yeah, he was supposed to be here today. I messaged him. I don't know what happened. But since you talk about that, labs are not going to be starting until probably next week. What is going to happen is that the intention is to use Multisim to look at lab exercise. So he's going to post the lab exercises right into this class chat, not the chat, the classroom where the class material is. He's going to post it. You're going to see them. You're going to be able to look at it. You're going to be able to do the labs in Multisim. And I think he is going to, on a phase basis, invite persons to come on campus because we have to control the space, albeit COVID is where it is. We have to control that space in terms of the amount of persons who can physically be in the lab at any one time. So you're not going to be just going to lab, but you'll be told, informed ahead of time, and you'll be doing most of the lab work using Multisim. You guys would have had Multisim from devices, right? Most of you.
Yes, sir.
Good. So it's also a similar thing you're going to be looking at. Doing the lab, getting your results. The lab exercises are going to be posted. And you submit. Don't submit the labs to me, please. I'm not the person who's going to be marking the labs. It's going to be Mr. Wright, okay?
All right, sir.
All right. I'm hopeful that next week we'll get him in class to talk to you. He did that for the Monday group. I hope that you get him in class to talk to you. Probably he had forgotten that we had a session this afternoon. But what I can just generally repeat that his approach is that he's gonna give you the labs, post them up here, you do the labs using Multisim. During your lab times, probably will be available. Mr. Wright, that is at that time to ask and to be asked questions. There's a design lab exercise that he's gonna be. It's already there. He's gonna be telling you and walking you through it, and probably that one, based on the experience with the other labs that you'd have done, you probably need to get on campus at a time and date that he will provide, that you can actually come in to your building of the lab that you'd have already designed, get your result and demonstrate to him what the scenario is and how you went about doing your design. In a nutshell, that's what I garnered from what he had said. But as I said, I will have him, God's willing, come and have a discussion in person. Well, so much for in person. Well, to you guys here, all right?
All right, sir. Have a good one.
Same to you and all your colleagues. Be safe, guys. Please do not. A matter of fact, the next time I come, I'm going to ask people in the class to just give me what you understood from what you read, specifically on those amplifier applications that I told you about, right? And what you did not understand, especially with the derivative of the equations, the gains for each of those. So everybody here should be able to tell me one takeaway that they got in terms of from their understanding of reading the posted or going to the posted information. And hopefully you'll understand it all, but if you didn't, you get a chance to post question that refers to what you did not fully grasp so that we can go through it. Am I clear?
Crystal, sir.
All right. All right, ladies, go have your dinner. I don't want to keep you to be hungry anymore. And remember the gentleman who is doing the recording, please share it to me included, all right? All right, have a good night, guys.